So this video is going to be going through the multiple choice practice prelim questions, most of which you probably will have already tried in class, but it's just to go over in case you've forgotten. So question 1, when 3.6 grams of butanol, which has a relative formula mass or a gram formula mass of 72, was burned, we had 134 kilojoules of energy released. So that's 3.6 grams gives us 134 kilojoules. Now it's asking, what was the enthalpy of combustion? Well, enthalpy of combustion, oh I'm sorry, that's quite blurry at the side. Enthalpy of combustion is the enthalpy when 1 mole is combusted. And 1 mole is 72 grams. So what you're going to be doing here is your 134 divided by your 3.6 multiplied by 72, the way you would do. And when you do this, you get a number which is 2,680. Now this is an enthalpy of combustion, and so enthalpies of combustion are always negative because it's exothermic reaction. So our answer is going to be C. In our next question, sorry, just trying to get this camera a bit better. Well, we have a mixture of sodium chloride and sodium sulfate. So you'd have to work out the formulas for these. NaCl is sodium chloride and Na2SO4. Now that's from Nat 5. So if you are in S6 and you're wondering, do that, I suggest you watch, if you're crashing, I suggest that you watch the National 5 videos in the National 5 YouTube playlist, Unit 1 on formula, and there will be a video which takes you through that. Now you're told that you have 0.6 moles of chloride and you have 0.2 moles of sulfate. Now if we look in each of these, the ratio is 1 to 1. So for every chloride, we're going to need a sodium. So that means we've got 0.6 sodiums from the sodium chloride. In this one, for every 1 sulfate, SO4, we have 2 sodiums. So that's going to be 2 times 0.2, which is 0.4. And when we add those two together, we get 1.0. So the answer to 2 is D. Those questions are really common. Right, our next question. Which one exists as discrete molecules? Where, well, boron, carbon, and silicon, and carbon and diamond specifically, those are all our covalent networks. Sulfur is our discrete molecule, and it is S8. Remember, you need to know that. For question 4 here, which of the following chlorides is the most ionic? So most ionic, what that means is most polar. Because remember, covalent bonds go on a spectrum from non-polar through polar, and then the very extreme is ionic. So the most ionic is the same as asking the most polar. Now, every single one of these has chlorine involved in it, and chlorine has an electronegativity. If we look up page 12 of the data booklet, it has an electronegativity of 3.2. So all these other ones, we just need to compare how far away they are from 3.2. Well, lithium has an electronegativity of 1.0. Cesium, let's find cesium. Cesium has an electronegativity of 0.8. Beryllium has 1.6. And calcium has, it also has 1.0. So you can see these two have the biggest gap, the biggest difference, so they're going to be the most polar. So it's going to be our cesium chloride. You could also work that out from where they are on the periodic table. So chlorine's near the top right, anything near the bottom left should have a really low electronegativity. Now our next question, which is the second ionization energy? Now remember, the most important thing with ionization energy is 1, everything has to be a gas. Then also, it's only 1 electron being removed each time. And if it's the second ionization energy, we're ending up with 2 plus. So the two that have 1 electron both start 2 plus, but only A is gaseous. And it starts plus to 2 plus with 1 electron, everything gaseous. So 5 is our second ionization energy. Remember, whatever number ionization energy is the charge that it ends up, and you're only losing 1 electron, so you have to start with only 1 charge down. So if you're going to 2 plus, you need to start with plus. Right, moving on to the next question. So the next question is a potential energy diagram. Now remember, on these, our reactants are on the left-hand side, our products are on the right-hand side. It's asking us for our activation energy for the forwards reaction. So forwards is going from reactants to products. Activation energy is that difference between the highest point, the activated complex, and the reactant. So that is our EA. So that's going to be Y minus X, which is answer C. Question 7, and again, apologies for the shadows on this camera, it's not the best video. We've got spikes showing our different ionization energies, and it's asking us which group the element belongs to. Well, if we see here, this is where we get our big jump between the third and the fourth. And we get this big jump whenever we have one less energy shell. And we're getting that jump on the fourth ionization energy. So that's when we have lost it, which means we are in group 3. When the jump occurs between 3 and 4, elements in group 3. If the jump were to occur between 1 and 2, the element would be group 1. If it occurred between 5 and 6, it would be in group 5. Question 8 is definitely an A-type question. I've got it handwritten. Your sheet should have it written nicely for you to look at. Which of the following contains the same number of atoms as 16 grams of helium? So number of atoms, atoms is related to moles. So atoms is related to the number of moles. So you can think about that as which one of these has the same number of moles of atoms as 16 grams of helium. So we need to think about how many atoms of helium are there, or how many moles of helium. Well, helium has a mass number of 4, so that would be its GFM. So 16 divided by 4 tells us we have 4 moles of He. Now for all these other ones, we're going to need to think about how many moles there are of each chemical, and then how many atoms there are in each chemical. So methane is CH4. Oxygen is O2, ammonia is NH3, and argon is just AR. So we need to work out how many moles of the chemical, and then how many moles of atoms. So in this one, we've got 5 atoms. So for every mole of methane, we'd have 5 moles of atoms. For oxygen, we have 2 atoms of oxygen for every 1 oxygen molecule. So for every 1 mole of this, we'd have 2 moles of atoms. There's 4 atoms in ammonia, so for every 1 mole of ammonia, we have 4 moles of atoms. And argon is monoatomic, so the number of moles of argon equals the number of atoms in argon. So the GFM of methane is 16. So 16 divided by our 16 here is 1 mole. And remember, there's 5 atoms here, so that means we have 5 moles of atoms. Oxygen, so the GFM of oxygen is 32. So 16 divided by 32, sorry, I've written 22 there. 16 divided by 32 is 0.5 moles. Now remember, there's 2 atoms of oxygen for this. So when we multiply that by 2, that gives us 1 mole of atoms. With ammonia, the GFM is 17. So 17 divided by 17 gives us 1 mole. And because there's 4 atoms in ammonia, when we multiply our 1 mole by 4, that gives us 4 moles of atoms. And finally, argon. Well, the GFM of argon is 20, I think. Oh, I'm just trying to find it on the data booklet. Sorry. Argon, oh, it's 40. So the GFM, well, 39.9 is 40. So we've got approximately 0.5 moles, and there's only one atom in each argon, so that's 0.5 moles of atoms. So we had 4 moles of helium, 4 moles of atoms in ammonia. So our answer was C to that one. That is definitely an A-type question. So I'll slide that over so you can read that better, because I know it's getting a bit blurry on the right-hand side. Right, next. Question 9. So what we have is a molar volume question. We're told we're using 20 of ethane and 100 centimetres cubed of oxygen. What's the final volume of gases? Well, let's look at our ratio. It's 1 to 3.5 to 2. Now, water is a liquid, so we don't need to worry about it because it's not a gas. Now, we are using 20. If we use 20 of this, 3.5, times 20 is 70, and we would make 40 of this. Now, what we started with, or what we had, was 20, 100, and we started with none of this. So if we do the maths, this is what we had, and we'd have 30 left over of oxygen, and we would have 40 of our CO2. So when we add those numbers together, we get 70 centimetres cubed. So our oxygen was in excess, and our answer to this one is B. Right, next question is to do with equilibrium. In a reversible reaction, equilibrium is reached. Well, equilibrium, before we even look at the answers, equilibrium is when the rate of the forwards reaction equals the rate of the reverse reaction. So I'm going to look and see if anything says about that. So I've not got anything about rates being equal. So let's read through all the others. Molecules of reactant cease to change into molecules of product. Well, that's not true because both reactions are still happening. Concentrations of reactants and products are equal. Well, the rates are equal, but the concentrations are very, very, very rarely equal. The concentrations of reactants and product are constant. Well, if the rates are equal, the amount of reactant turning into product and the amount of product turning into reactant is always going to be the same, so the concentrations will be constant. So that's correct. Now let's just check. The activation energy of the forward reaction is equal to the reverse reaction. Well, that's never true. You've always got one has a higher activation energy than the other. So that one's not true. So it leaves us with C. At equilibrium, concentrations of reactants and products are equal. Right, next question here, question 11, is Hess's law. Now we're wanting to do X. So that would mean if we're going from here to here, that's going to be the same as doing this and then doing this. So this arrow, we know that one is minus 393.5. This one, we've changed the direction of the sign, so we just need to change the direction, change the arrow's direction, so we change the sign. So it's going to be minus 393.5 plus 283. So it's going to be negative 110.5 when we do that. Answer B for question 11. For 12, so this is oxidation. So oxidation is loss of electrons. Now electrons are negative, so if you get rid of electrons, your charge goes up. Because if you get rid of one electron, you go from 0 to positive. Okay, so we're going to look for something that has started at a lower charge than it finishes. So let's just see Hg in HgCl2. Well, the Cl is Cl minus. Your Hg, there's two Cls, so that's going to be Hg2 plus. Here we've got Cl, so Cl again, Cl minus, and our SN is SN2+. Now here we've got Hg, which is mercury. That's a liquid. It's an element. Every element is 0. So it's just going to be Hg0. And here we've got our Cl. So Cl again is -1. It's always -1. But to balance that one out, Sn is going to have to be 4+. Okay, now if something's being oxidized, it has to be a reactant. Okay, so it can't, nothing in our answer can be anything on the right hand side. So we can't have Sn4+, and we couldn't have Hg0, but that's not there. So then we're looking for something where the charge has gone up. Well, Hg has gone from 2+ to 0, so that's gone down, so that's not been oxidized. Our Cl-, well, it's Cl- here, here, and here, so it's not changed. And our Sn2+ went from Sn2+ to Sn4+, so it was oxidized, it went up. This next question is a bit unfair. Kind of have to do it by process of elimination. So let's look. This is HCl. So HCl, hydrochloric acid, reacting with excess zinc. Excess zinc means that all the acid is reacting. Okay? So all the acid is reacting. So this is going to have 1 mole per litre H+ ions, 1 mole per litre chloride ions. So let's look at, and we're going from 1 to 2. So 2 is faster. So if it's faster, we have to think about any factor we know that could increase rate of reaction, but it's finishing at the same point. Now zinc reacting with HCl is going to ZnCl2 plus H2 gas. It's producing hydrogen. Now the amount of hydrogen that's being produced, because the zinc is in excess, is being determined by the acid. So we need, if we have more acid, we will make more H2. So we need the same concentration of acid as we have here. Okay? We need the same concentration of acid to give us the same product, but we need something that would make it go faster. Right, so excess zinc with hydrochloric acid at 2 times the concentration. Well, if it's 2 times the concentration, we're going to have 2 times the H+ ions. So it's going to produce more hydrogen gas. So that one cannot be true. Sulfuric acid, 100 centimeters cubed, 1 mole per litre. Well, sulfuric acid also, because it's H2SO4, that's going to have 2 times the amount of H+. So it's going to make more hydrogen gas. Ethanoic acid reacting with zinc. Well, ethanoic acid reacting with zinc, that's still, it's got the same amount of H+ ions because ethanoic acid is CH3COOH. So the concentration of H+ is the same, and we're reacting with the same metal. So let's try the next one as well, but this is a possibility. Next one, it's the exact same, so we've got the same amount of H+, it's the same acid, but we've changed the metal. So what would make it faster? Zinc with a different acid or magnesium with the same acid? Well, magnesium from National 5 is a more reactive acid, so it one would react faster. Ethanoic acid, we know that's vinegar. Vinegar is actually a weaker acid than hydrochloric acid, so it would react slower. So the answer to this one is D. Now that's a really, really difficult question. I have to say that is a really, really difficult question. And so we're showing you it, but it is unlikely something like that would come up again. But we're just showing you that as the worst case scenario. Right, as the relative atomic mass in the halogens increases, so essentially as you go down the group, does the boiling point increase? Well, you'd have to consult the data booklet. So in the data booklet, if we look at our melting and boiling points, the melting and boiling points increase some of the way, but then they actually don't fully increase. So the boiling point, well, the boiling point does increase. First ionization energy, so the boiling point does increase. You go from gases to liquids to solids, so that one is correct. Atomic size decreases. Well, we know atomic size increases as we go down the group. First ionization energy increases. Well, we know that decreases down a group. So that's wrong. Density. Now, density we would need to look up in the booklet. So let's just look. It's on page 5. So the density of fluorine is very, very, very low. Chlorine is actually a little bit higher. So the density does increase there. Then we've got fluorine, chlorine, bromine. So bromine, the density of bromine is 3.1, and the density of iodine is 4.93. So that's still increasing. And then we've got astatine, where it's unknown. So that one isn't very clear, because it does look as though the density does increase going down the group. But because astatine's unknown, that's a question mark. So the only one that's definite. So that's not a very nice question, but definitely the boiling point is increasing as you go down the group. So the issue one is just that we don't have astatine's results for density. Question 15. For two atoms to form a non-polar atom, well, polarity, if it's non-polar or covalent bond, we're talking about electronegativity being the same. So that one's B. Question 16. Which one would an increase in pressure cause the equilibrium to move to the left? So if we increase pressure, the system wants to decrease moles of gas. And we're wanting it to move to the left. So we're wanting one where there's less moles of gas on the left-hand side compared to the right-hand side. Let's make sure we don't look at anything that's not a gas. So in this one, we've got 2 and 2, so pressure won't affect it. We've got 2 here and 4 here. So that one does have less moles of gas on the left-hand side, so that would be our answer. Just going through, question C, 3 and 3, so equal moles of gas. And then in D, it's 4 on the left-hand side, 2 on the right-hand side, so that would go to the right. So definitely B. Which is never found in elements. So elements, every atom in the element has the same electronegativity. So you cannot get anything polar. So you cannot get a polar covalent bond, you cannot get a permanent dipole, or hydrogen bonding, and you cannot get ionic bonding. All of those come from having differences in electronegativity. In elements, you don't have that, so you can never get anything that is polar. Strongest reducing agent. Now, in the data booklet, our strong reducing agents are found on the top right. So reducing is on the top right, and oxidizing is on the bottom left. So if you look on page 13, at the top right, we have lithium. So it's our strongest reducing agent. So increasing temperature. So increasing temperature, well, activation energy, the only thing that affects that is a catalyst. So that's not going to do anything. An increase in the enthalpy change, well, enthalpy change is fixed. You cannot change that. Decrease in the activation energy, well, again, a catalyst is the only thing that can change activation energy. More molecules per second forming an activated complex. Well, that's what's related to the rate. So definitely that is affected by temperature. More activated complexes forming means the reaction will go faster and temperature increases rate. So that would be our answer there. Right, another question here related to equilibrium. Oh, no, it's not. It's actually atom economy and percentage yield. So it's a Haber process. So equilibrium lies to the left. So equilibrium lies that way. So we're making more reactant than product. Atom economy, well, we've only got one product, so our atom economy is definitely high. So we can eliminate C and D. If you've only got one product, your atom economy is 100%. If the equilibrium lies to the left, we've got not very much product, so the percentage yield is going to be low. So our answer to this one is B. Question 21. Which one will both result in an increase in the rate of reaction? Okay, decrease in activation energy. That definitely increases rate of reaction. An increase in frequency of collisions. More collisions means more likely to have a reaction. So those both do. So this one looks like it's our right answer, but let's just check. Increase in activation energy, no, so we can eliminate that one. An increase in temperature, that would increase rate. Increase in particle size does not, so we eliminate that one. Increase in concentration, that one would increase rate. Decrease in surface area is the same as increasing particle size, so that one would not. So definitely A is our correct answer there. Right, question 22. It's working out your number of H plus and H2O. So this is your eat only hot curries method. Element, oxygen, hydrogen, charge method. So, and we're wanting to find out the number of H plus, so that's our number that's coming first, and our H2O, that's the number that comes second. So when we do this, we've got two iodines here, so we need two iodines here. We've balanced our elements. We've got 6 oxygens here, so we need 6 H2O to balance that out. So we can eliminate B and C because we know we need 6 oxygens. 6 waters, sorry. We've got 12 hydrogens here, so we would need 12H plus here. So that would mean D is our answer. And then finally, just checking that we can complete this, there's no charge on the right-hand side. Together, these add up to give us plus 12 minus 2, so that's plus 10. So we would need 10 electrons to make that completely balanced half equation. Right, so this one, question 23 is bond enthalpies. So hydrogen and chlorine react explosively. One step is shown here. So you've got H2 plus chlorine, just one chlorine atom, going to HCl plus H plus. So what would the enthalpy change be for this? Now remember, bond breaking, it's always products minus reactants. Reactants minus products. I always get this one wrong. Reactants minus products, because breaking bonds is positive, and that's your reactants. You're breaking those bonds. You're making this bonds. That's exothermic, so that's why it's reactants minus products. So in our reactant, we have HH, and we are taking away our HCl. There's no bonds here. There's no bonds here, because they're just single atoms. So it's HH minus HCl, which is C. Right, next one is a chromatography question. We've got compound X plus compound Y gives us a fragrance compound. So that's 1 plus 1 gives us 1. So that's sort of our ratio. After 1 hour, sample is removed and compared with pure samples of X and Y. Which of the following chromatograms shows that the reaction has produced a pure sample of fragrance compound? So if the product is pure, pure would mean only one spot. And pure product means that it cannot be a spot that matches either of the reactants. So A, well, X is here, Y is here, so it's not a reactant, and we've only got one product. So this looks correct. B, we've got two spots, so it's not pure, and also they match the reactants, so it's not that. This one, we've got something new that's formed, but we've got a second product, so it's not pure, and that matches X. On this one, something's happened. It doesn't match either of the reactants, but it's not pure, so it's not that one. So we were right with the first one. One product that's different from either reactant. Finally, we have question 25. Now, question 25 is a little bit of a problem-solving question. So, when a catalyst is used, the activation energy for the forward reaction is reduced to 35 kilojoules per mole. Right, so that's our activation, and that's now 35. Okay, that's 35. Now we want to know the activation of the reverse reaction. So we want to know this energy here. So how are we going to work that out? Well, we could see the difference between these two was 30. So we could just add 30 on here because we know that difference there is 30. So if we add those two together, it gives us 65 as our answer. Okay, because this extra energy was worth 30. That's not going to change. That's your enthalpy change. So that gives you it. So I know that video is not the easiest to see. I do really apologize for the shadows. I could not avoid it. I'm really, really sorry, but hopefully that helps you go through the answers to that.